Good day. For those of you who do not know me, my name is Douglas Harder, and this topic we're going to look at using the golden ratio search for finding local extrema. So in this topic, we will review the idea of using bisection for finding a minima. We will then describe the idea of using trisection. We will then consider increasing efficiency by halving the number of function evaluations. Consequently, this will introduce the golden ratio and the reciprocal thereof. We will look at an implementation of this algorithm and give an example application. Now you will recall that for the bisection method, what we did is we guaranteed that there was a root on a particular interval. Suppose that you're aware that there is a unique local minimum on an interval from A0 to B0. We're going to develop a bracketed technique that attempts to reduce the width of this interval in a manner that is efficient. All right, so let's say we've iterated a few times and we know that there is a minimum on the kth iteration of this algorithm. So we know that there is a unique minimum on the interval from AK to BK. Let's mimic the bisection method and calculate the midpoint. So the midpoint is the average of the two endpoints at the kth step. Question: does knowing the value of the function at this midpoint help us in any way to reduce the width of the interval over which we're searching? Well, suppose this is the actual function we're trying to minimize. Well, if we evaluate the function at the midpoint, we know it's less than either endpoint, but does it suggest that the minimum is on the left-hand interval? Not really, because after all, the function we're trying to minimize could look like this, and evaluating that function at the midpoint would give you approximately the same value. So evaluating the function at a single point in the middle is not going to help you reduce the interval. We don't know whether or not the minimum is on the left-hand interval or on the right-hand interval. All right, so it seems that one point is not enough. So unlike the bisection method, which bisects the interval, let's trisect the interval. So we're going to take the interval from A to B, and we will calculate a left-hand endpoint, which is 1/3 of the distance into the interval. However, rather than describing this as being 1/3 of the distance into the interval, I'm going to just describe it as 2/3 the distance from the right-hand endpoint. So L sub k is the point B sub k minus 2/3 the width of the interval. Similarly, we're going to calculate a right trisected point, so a point that's 2/3 into the interval, and once again, I will be representing this as the left-hand endpoint plus 2/3 times the original distance. All right, so now hopefully we can get a little bit more information as to which subinterval the minimum may actually be on. All right, so taking a look at the left-hand image, if f evaluated at the left interior point is less than f evaluated at the right interior point, then we can actually restrict the interval onto which the minimum exists to go from A sub k to R sub k. Consequently, for the next iteration of this algorithm, A sub k plus 1 is assigned A sub k, but B sub k plus 1 is assigned R sub k. However, if it is the right interior point that has a smaller function evaluation, then we can restrict the minimum to at least going from L sub k, the left interior point, to the original B sub k. Consequently, in this case, for the next iteration of this algorithm, a sub k plus 1 is assigned the value of the left interior point, and b sub k plus 1 is b sub k. Now, can we do better? Well, not really. Consider both of these images. In both of these images, the function evaluated at the left interior point is less than the function evaluated at the right interior point. Consequently, well, that's about it, because notice on the left example, the minimum appears to be to the left of the left interior point, but in the right-hand image, the minimum appears to be slightly to the right of the left interior point. So we cannot restrict the interval any more than by reducing it by a factor of 2/3. So if the width of the interval was b sub k minus a sub k, after one iteration, the width of the new interval we're searching for, or searching on, is 2/3 b sub k minus a sub k. That is, we've reduced the width of the interval by a factor of 2/3. That's not as good as the bisection method. The bisection method halved the width of the interval. At this point, we can only reduce the width of the interval by a factor of 2/3. Okay, so consequently, with each step, we have reduced the width of the interval by a factor of 2/3. And in order to reduce the width of the interval by a factor of 2/3, we require two function evaluations. We have to evaluate the function at both the left and the right interior points. You will recall our previous discussion that function evaluations are likely the most expensive operation we'll have to deal with. In general, most of these numerical algorithms are relatively straightforward. However, every time we call a function, that may actually be a very expensive operation. So the question is, can we reduce the amount of work required? That is, can we reduce the number of function evaluations? The problem is that by trisecting the interval, suppose that we restrict the minimum to be on the left 2/3, so from a sub k to r sub k. Well, in this case, the other point we evaluate the function at, L sub k, the left interior point, that happens to be dead center of the new interval going from a sub k to r sub k. So do we evaluate the function at a point to the left or to the right of that if we wanted to reduce the number of function evaluations? Well, it's not really clear. We don't know whether or not if the minimum is on the left side of the L sub k or on the right side of the previous L sub k. So we really can't do anything other than simply start over again and trisect the interval a sub k to r sub k. Okay, instead of dividing the interval up into thirds, let's divide the interval up into fifths. Now, we're not going to evaluate the function at each of these points. We'll only evaluate the function at 2/5 into the interval. Alternatively, 3/5 the width of the interval coming in from the right-hand side. And we'll also evaluate it at 3/5 coming into the interval from the left-hand side. So once again, a sub k plus 3/5 the width of the original interval. All right, now we can do exactly the same thing we did before. Compare the value of the function at both the left interior point and the right interior point, and that will tell us if we're to restrict the interval to a sub k to r sub k or L sub k to b sub k. All right, having divided the interval into fifths and having evaluated the function at the two interior points closest to the center, we can see in this example that the value of the function at the left interior point is less than the value of the function at the right interior point. Consequently, with the next step, we will restrict ourselves to the interval from a sub k to r sub k. So a sub k plus 1 is still a sub k, while b sub k plus 1 is now r sub k. We're going to do the same thing. We will divide this interval into fifths and evaluate the function at each of these two interior points. Now, notice something quite interesting. The original point L sub k is really close to the newly calculated point R sub k plus 1. So consequently, we note that R sub k plus 1 is approximately equal to L sub k. Would it be possible to choose L sub k and R sub k plus 1 so that they coincide? So if we're restricting ourselves to the left 3/5 of the interval, the question is, can we choose a scaling factor so that the right interior point with the next iteration equals the left interior point of the original iteration? Well, basically, we want to choose a scaling factor s such that the left interior point is b sub k minus some scalar times the width of the interval, and the right point is a sub k plus that scalar times the width of the interval. When we did trisection, s was equal to 2/3. When we divided the interval into 5, we chose s to be equal to 3/5. Well, let's suppose that we update the right endpoint. So b sub k plus 1 is assigned r sub k. Well, with the next iteration, r sub k plus 1 is the new a sub k plus s times the new interval. But wait a second. The next a was the previous a, and the width of the new interval is s times the width of the original interval. And therefore, this is just a sub k plus s squared times b sub k minus a sub k. That is, a sub k plus s squared times the width of the original interval. Consequently, we want the left-hand point at the original iteration to equal the right-hand point of the next iteration. So we want to solve that equation below. Thus, if the next right interior point is to equal the left previous interior point, then this equation, which we derived on the previous slide, must be satisfied. All right. So in solving an equation, we convert this into a root finding problem. Let's bring everything to the right-hand side and collect similar terms. Now notice that we have almost a common factor of b sub k minus a sub k. In fact, if we multiply that last term by -1, we actually do have a common factor of b sub k minus a sub k. So therefore, for that equation above there to be 0, or to be satisfied, we require to find a root of this expression. But b sub k minus a sub k will always be non-zero, since b sub k and a sub k are always different. Consequently, the only way that can be 0 is if we have s satisfying a root of s squared plus s minus 1. Okay, so that's a quadratic equation, so s must equal this value here. which equals this value here, -1 plus or minus root 5 over 2. Now, only one of these two values is positive, and s should be positive, and it is this one here, -1 plus root 5 all over 2. Well, this is equal to root 5 minus 1 over 2, which is approximately 0.618034. Consequently, if we use this value of s, root 5 minus 1 all over 2, notice that with the next iteration, we see that the right interior point equals the left original interior point, and therefore we can use the same function evaluation. Consequently, we only have to perform one additional function evaluation, and that is at the new left interior point. Now, this is called a golden ratio search because this is the golden ratio above here. It happens that 1 over the golden ratio is equal to this value here, and looking at those two, you will see that 1 over the golden ratio is equal to the golden ratio minus 1. There's a few other nice properties. The golden ratio squared is equal to the golden ratio plus 1, and that is a consequence of it being the root of the equation we just saw. All right, so consequently the two interior points divide the interval into a golden ratio. As in one further aside, the golden ratio cubed is twice the golden ratio plus 1. Thus, if we use this reciprocal of the golden ratio at each step to divide the interval, notice that with each iteration we reduce the width of the interval by a factor of the reciprocal of the golden ratio. However, this requires only one function evaluation. Therefore, with two function evaluations, we can reduce the width of the interval by 1 over the golden ratio squared. And so that is reducing the width of the interval by a factor of approximately 0.381966. You will recall that when we did trisection, we needed two function evaluations. And with two function evaluations and trisection, we were only able to reduce the width of the interval by 2/3, or 0.6666. Consequently, for the same number of function evaluations, likely the most expensive operation in any numerical algorithm, we can converge much more quickly if we use the golden ratio. Now let's define a function that calculates this golden ratio search. The first argument is the function we are trying to minimize. The next two arguments, a and b, define the interval on which we are finding the minimum, and we are assuming there is a unique minimum on the interval from a to b. The epsilon step size is the maximum error we're willing to tolerate, sort of. Epsilon absolute is the maximum error in the minimum value, how low it is, and then the maximum number of iterations. So first, let's assert that a is less than b. Next, we will define inverse phi to be the reciprocal of the golden ratio, so the value of approximately 0.62 and change. We will now define the width to be the width from the distance from a to b times the inverse of the golden ratio. All right, so now x1, the left interior point, will be b minus this width. x2 will be the right interior point, which is a plus this width. We will have two local variables, f1 and f2, which are the function evaluated at the left and right interior points. And we're just going to assert that both f1 and f2 are real and finite, not infinity or not a number. All right, so now we're going to iterate a maximum of max iteration times. First thing we're going to do is we're going to reduce the width of the interval once again by multiplying the width by the inverse of the golden ratio. All right, now we're going to look at the values we have. If f1 is less than f2, then the minimum is going to be somewhere between the left endpoint A and the right interior point. Okay, so if the width as currently defined is less than epsilon step, that means the maximum error will be width. Then if also the difference between f evaluated at the left and right interior points is sufficiently close, then we will return x1 and the value at x1 as being the minimum. Otherwise, we will set b to be x2, x2 is assigned to be x1, f2 is assigned f1, x1 is now b minus the new width we calculated above, and f at the left interior point is f evaluated at that point. So there's our one function call. Again, we're going to assert that this value is finite. All right. Alternatively, if f2 is less than f1, we will more or less perform the same operations. We will check if the conditions for terminating are met. If so, we will return x2 and f2. Alternatively, we will update. So the left-hand endpoint will be what was the left interior point. The left interior point now becomes what was the right interior point, and we calculate a new right interior point and evaluate the function at that new right interior point, checking again to make sure that it is finite. The only other case is where f1 equals f2. Now, if the width is less than the epsilon step size, then we will return a pair where we estimate the minimum as being the average of the two interior points. We don't have any better estimate, so might as well give the midpoint. Now, alternatively, we're in a mess right now because we're not really sure where the minimum is. The minimum actually could still be slightly to the left or slightly to the right, but at this point the function is so flat that the function has the same value at both interior points. Consequently, what we will do is we will assume that the minimum continues to be somewhere on this interior. So now we just update A and B to be the two interior points. We now perform two steps of the golden ratio search by multiplying the width by the inverse of phi twice. And now we calculate two new interior points, x1 and x2, based on this new width and evaluate the function at them. And we check to make sure that these new values are indeed finite. At this point, we have finished our loop. And if we ever do finish that loop, that means we did not find a minimum. And so we're just going to return a pair of not a number. All right, let's use the golden ratio search to find the minimum of the function e to the negative 2x minus e to the negative x, starting with the interval from 1 to 2. The width of this interval is 1, And therefore we can calculate the two interior points by calculating 2 minus the reciprocal of the golden ratio and 1 plus the reciprocal of the golden ratio. So that gives us the first 4 points, and the value of the function at those 4 points are shown there. Now, of those 4 points, the left interior point is the one that is least in value, and therefore it is the minimum, and therefore we will assume that the minimum lies between the left endpoint and the right interior point. Consequently, we must calculate a new left interior point, now using the reciprocal of the golden ratio squared. All right, now once again we look at the two interior points, and once again the right interior point is still the minimum, and therefore we must assume that the minimum appears on the interval starting at the left interior point going to the right end point. All right, so once again the left interior point becomes the left end point, the right interior point becomes the left end point, and the right end point remains unchanged, and we use with the golden ratio once again to calculate the right interior point, and we evaluate the function here. Well, as it happens, the left interior point is once again the minimum, and therefore we assume that the minimum lies on the interval from the first to the right interior points. And once again, we calculate a new left interior point. And we would proceed from here on in, going forward step by step, with each step reducing the width of the interval by the reciprocal of the golden ratio, so by approximately a factor of 0.62, and also we are only performing one function evaluation per iteration. So following this topic, you now understand a bracketed method for finding a local minimum. You are aware of the usefulness of using the reciprocal of the golden ratio to calculate the location of the interior points. You've seen an implementation and looked at an example. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!